Good. So yeah, I'm happy to be able to participate in Serge's celebration, and I'm sorry I couldn't be there in person. So Serge and I go back a really, really long time. It all started at USC in the early 80s, when we were both PhD students of Seymour Ginsburg, and where we also met Rick Hull, our future co-author on the Alice book. So when Serge graduated, he took a job at INRIA, and in 1983, he invited me to visit. And this was the start of a long, long sequence of visits that stretched over 40 years. And this was the beginning of 40 years of friendship and 40 years of research adventures. And I want to tell you a little bit about the research adventures. Okay, so according to DBLP, Serge and I co-authored about 53 publications. So the choice is difficult. What I decided to do is take a trip down memory lane and tell you about some research that we did in the late 80s and early 90s. And this includes some of my favorite results with Serge. So the starting point for this line of research was a very basic question that we as young database researchers asked ourselves, which is what is special about database computation? And our answer was, what's special is computing with abstraction. So what do we mean by this? Well, the source of abstraction in database is simply data independence, probably the most fundamental principle underlying databases. So data independence says that the logical level and the physical level are independent of each other, which means that queries are posed against the logical level and cannot access the physical level. And it turns out that this has dramatic impact on expressiveness. So this was first highlighted by results by Immermann and Vardy on fixed point queries. So let me just remind you what these are. So there are two classes of queries which are particularly central, fixed point and while. Fixed point is first order augmented with an inflationary fixed point operator, and while is first order augmented with a non-inflationary fixed point operator. And Immermann and Vardy showed that there's a very puzzling behavior of these languages. So fixed point cannot express very, very simple queries, but on the other hand, it expresses exactly the polynomial time queries if an order is available. And similarly for while cannot express very simple queries, but it expresses exactly p-space with an order. Good. So what's the significance of order in the database context? Well, it can be viewed as a metaphor for accessing the physical level. Right, so the physical level would certainly provide the information that would be given by this postulated order. And these results by Immermann and Vardy show that there's a basic mismatch between query languages and classical complexity classes. And the source of the mismatch is that queries and Turing machines compute very differently on a database. So queries act directly on the database, on structures, whereas Turing machines act on encodings of structures. And in order to take a database and get a string out of it, you need some additional information in the form, let's say, of an order. Okay, so this led to the idea of perhaps defining an alternative computing device that works more like queries. And this led us to such a computing device, which we call relational machines. So what are relational machines? So they have a Turing tape, just like a Turing machine. They're endowed with a relational store that contains the database input and some work relations. And they can manipulate the relational store using first order means. And they can also ask first order questions, Boolean questions on the store. So this looks much more like a query computing device in the sense that it acts directly on structures, on databases. Okay, so now we would like to define complexity classes using this relational machine. the question is whether this overcomes a mismatch with classical complexity classes. And notice that this model is similar in spirit to, embedded SQL, where a full programming language interacts with a database through SQL queries. Okay, so let's see how can we define complexity classes based on this machine. So here we run into a tricky question. What should be the measure of the input? So for classical complexity classes, the measure is just the size of the input. But this doesn't really work here because a relational machine does not have full access to the database. It can only access a database using a certain class of first-order queries, and this allows it to find out only limited information about the database. And in particular, it cannot distinguish between large databases and small databases. So the key idea here was to define complexity classes, the measure of the input, relative to the discerning power of the machine. I'm not going to go into details, but this was really the key idea. So this gave rise to so-called relational complexity classes, for example, relational polynomial time, relational polynomial space, and so on. So here are the main results. So first of all, the mismatch between the languages and complexity disappeared. So fixed point expresses exactly relational polynomial time, while expresses exactly relational polynomial space. And moreover, there are very interesting connections with classical complexity classes. So the relational classes are included, strictly included in the classical counterparts, but their inclusion structure is exactly the same. So p time is equal to p space if and only if relational p time is equal to relational p space. And if we put everything together and remove the intermediate relational complexity, we get this theorem which says that fixed point equals while if and only if p time is equal to p space. And this was a result that was quite surprising at the time for several reasons. So although the question of the relationship of fixed point and while was open, it was widely believed that they're different and that it should not be very hard to prove that while is more powerful than fixed point. So this showed that this is not the case. If you solve this problem, you solve the problem of p time versus p space. Okay, so next we extended these results together with Moshe Vardi to more complexity classes and more fixed point logics. So basically, we looked at classes between polynomial time and exponential time. And the results are analogous. So the relational complexity classes are strictly included in the classical counterparts. The inclusion structure is the same. And for each relational complexity class, there are fixed point logics that correspond exactly to the complexity class. Now, these are variants of fixed point logics. I'm not going to go into details, but they vary by control, deterministic, non-deterministic, or alternating, and by the type of iteration, inflationary or non-inflation. Okay, so again, if you remove the relational complexity classes here, what you get is so a family of fixed point logics that have exactly the same inclusion structure as the classical complexity classes. So this reduces some of the most tantalizing open problems in complexity theory to relationships between fixed point logics. Okay, good. So let's go back to the original result by Immermann and Vardi. So basically, the result says that the presence of order can overcome limitations in expressive power, and the computational role of order is as a way to break symmetries, right? So, for example, the definition of a computable query requires to take a database and transfer it to a Turing tape as a string, and the order is helpful to overcoming this impedance mismatch between databases and Turing machines. And this impedance mismatch actually occurs in practical languages as well, as we'll see. So the question is, what if order is not available? And the answer is that in that case, the information necessary to break symmetries can be simply made up, and it can be made up using non-determinism. So the idea would be to have a non-deterministic data transfer from databases to the Turing tape. And this is not fantasy, it's actually something that happens in practice. So embedded SQL languages, for example, JDBC, allows non-deterministic data transfer back to Java. So here is a piece of Java code that assigns the result of a query to a so-called result set, which magically comes endowed with an order that can be iterated through. And this is really, non-determinism. It's hidden non-determinism. And non-determinism occurs implicitly in many practical languages. So all of this led us to ask what would happen if we make non-determinism a first-class citizen in query languages. Okay, so let me make this a little bit more precise. So a non-deterministic query is a query which on a given input has several possible outputs. And one can naturally define complexity classes of non-deterministic queries based on the time or space that each computation takes to compute its output. So for example, non-deterministic p-time and NDBP time are the non-deterministic queries for which each computation takes polynomial time. And it's important to note that this has nothing to do with NP, right? This is a class of non-deterministic queries. Good, so similarly, non-deterministic p-space can be defined analogously. All right, now there are many ways to add non-determinism explicitly in query languages, and we consider two main ways. One is to add an explicit witness or choice operator to query languages. So if phi of xy is a query, witness y such that phi of xy does the following. So for each x, it chooses non-deterministically one y such that phi of xy holds, and the result are the outcomes of all such choices. So if we add this witness operator to fixed point and while, we get non-deterministic versions of fixed point logics. So this is one way. Another very natural way is to do this in data log. So to take data log and give it non-deterministic semantics. Now this can be done very easily using a very basic idea, which is to just fire one rule instantiation at a time. So here you see an example of a rule with negations in the head, which stands for deletion. And what this does is it computes all, let's call them orientations of a graph G. So for every cycle, A, B, B, A, it chooses non-deterministically one of the edges. And we defined variations of these languages based on their features. So data log neg is data log with negation in bodies and deletions in heads. Data log neg is deletions, negations in the body. And this variant adds universal quantification on bodies of rules, and it's a kludge that's needed for technical reasons. So in terms of expressiveness, it turns out that these languages capture precisely non-deterministic complexity classes. Okay, so NDBP time and NDBP space, and very pleasingly, these are also equivalent to the non-deterministic fixed points. So this is a nice robustness property, which looks very nice. Okay, so a consequence of this is that non-determinism helps in expressing more deterministic queries. And this was one of the starting points in considering non-deterministic queries. We wanted to see if they can overcome the mismatch with complexity in the same way as order. So let's make this precise. So suppose we have a non-deterministic language. Consider its deterministic fragment, that of L, which consists of the queries which are expressed by L and are actually deterministic. So from these results, we get that the deterministic fragments of the languages are exactly deterministic p-time and p-space. So it is the case that non-determinism can actually overcome expressiveness limitations, much like order. Okay, so if you look at the last result, this is intriguing, right? It suggests that maybe these provide languages for p-time, which would be remarkable. But unfortunately, that's not the case because it's undecidable if a query belongs to the deterministic fragment. Okay, good. So these were some of the more fun results, in my view, that Serge and I got together, some of my favorites. They were tons of fun. Of course, I would be remiss to not mention Alice, which was also tremendous fun and a very satisfying adventure on its own. There's a lot to say about Alice, but Alice has already been celebrated twice, once for her 10th birthday at Sigmod Pods 2004 in Paris, and second time on her 25th birthday at ICDT 2019 in Lisbon. So now it's time to say happy birthday to Serge, and I look forward to hearing about his plans beyond database research. So thank you, Serge, and happy birthday.